Hello everyone, this is lecture 4 in week 8. So, in the previous 3 lectures we learnt about solving constraint optimization problems which has equality constraints or inequality constraints using augmented Lagrangian methods, right. So, and we will start with a practical example that we worked out long back in the very first week of this course, right. So, that is the consumer utility maximization problem. Okay. So, if you recall the problem, it is this. Okay, I mean this is actually in 2 dimensions. So, if you recall the more general problem, this is the more general problem that we have here, right, where we maximize some utility of the consumer, right, which is a function of x1 x2 dot xn. So, to recall what these x1 x2 xn are, so the consumer has n items to buy, right, and these are the quantities that he buys. So, he buys a quantity x1 for item 1, x2 quantities of item 2 dot xn quantities of item n. The price of each of these items are given by p1 p2 dot pn, right. So, this is the budget constraint. So, W is his monthly income, right. So, or wealth as you can call it, right. So, of course, he cannot spend more than his wealth. So, summation pi xi must be less than or equal to W, and of course, xi has to be non-negative. He cannot buy negative quantities of any items, right. So, this is the more general problem of consumer utility maximization, right. So, and we actually considered the utility to be the product of the quantities that he buys, right. So, x1 is the quantity x1 quantity of item 1, he buys x2 quantities of item 2 and so on, right. So, we we solved a problem analytically where he buys only 2 quantities sorry 2 items, and he buys x1 and x2 quantities of those items, right. So, we will consider an n item setting, okay, and instead of the product we will actually consider a slightly different utility, okay, and so what is that utility? It is the following. So, we are actually considering this problem. We minimize minus log x1 minus log x2 minus dot minus log xn. So, we consider the general n item problem, but the utility that he is maximizing is logarithm of the quantity of the first item plus the logarithm of quantity of the second item plus dot plus logarithm of the quantity of the nth item that he is going to buy, right. So, that is the utility that he is going to maximize. So, since we are considering a minimization problem, we are considering the negative of that. So, that is minimize minus log x1 minus log x2 minus dot minus log xn, okay. Of course, the constraints are the same. You have summation pi xi less than or equal to W equal to 1 to n, and xi greater than or equal to 0. So, I will write that as minus xi less than or equal to 0 for all I equal to 1 to n. Okay, so, there are n plus 1 constraints, all inequality constraints, and so this is the quantity that he is going to minimize. And now note that the problem that I considered here and the problem that was considered earlier are quite the same, because when you are maximizing x1 x2, it is equivalent to maximizing a monotonic function of x1 x2, right. So, log is actually a monotonic function in x, right. So, I have just considered log of the product of xi's, which is the sum of log of xi's, okay. So, both the problems are the same. I am just considering it this way because this is a convex optimization problem, no other reason, okay, fine. So, let us actually work on solving this particular problem, okay. So, I am going to maybe before solving it using Python, we will solve it by hand. It's not very difficult. Okay. So to solve it by hand, I would like you to observe something, right. So note that this quantity, this constraint that we have here. So this particular constraint, summation Pixi less than or equal to W, right. So this summation Pixi is an increasing function of x, right. So this is an increasing function of x, right. So and you can also see that log of x1 plus log of x2 plus dot 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 log of xn is also an increasing function of x, right. So the solution is never going to lie at a point where summation Pixi is strictly less than W, right. So that is because if you increase the values of xi, right, you will still satisfy the constraint summation xi Pixi less than or equal to W, and you are actually increasing the utility log of x1 plus log of x2 plus dot 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 log of xn, right. So I am doing this so that I am simplifying the problem, otherwise I mean, yeah, we may have to analytically it will be a little more simpler if I actually do this. Okay. So yeah, so the claim is that in fact, I mean, I think I have also argued why that is the case. So this constraint can be simplified to summation Pixi equal to W. Okay. So that is because if the right answer, the optimal solution of this particular problem occurs when summation Pixi is less than W, right. So by increasing xi is a little bit, I can increase the utility function, that is log of x1 plus log of x2 plus dot 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 log of xn, right. So that is certainly not the solution. The solution is going to occur in this plane summation Pixi equal to W, right. So yeah, so we can now rewrite this problem as minimize summation minus log xi I equal to 1 to n subject to summation Pixi minus W equal to 0 and minus xi less than or equal to 0, right. Okay. So this is a more simplified problem. Okay. Yeah, so now we can write down the Lagrangian, since we are actually solving it by analytically, right. Yeah, the Lagrangian will be minus summation log xi plus lambda into summation Pixi minus W minus summation mu I xi, all summations from I equal to 1 to n, right. So if we differentiate, I mean take the gradient of this with respect to x, you will have minus 1 by x plus lambda pi minus mu I. Okay. So if we assume all mu i's to be 0, right, so then we will have so yeah, this is for all I, right. So for all I equal to 1 to n. So we will assume mu i's to be 0 for the time being. Okay. And you can see that we have minus 1 by xi equals lambda pi, sorry 1 by xi equal to lambda pi, right. So or I will write it as lambda equal to 1 by Pixi for all I, right. So what this tells us is that Pixi is actually a constant. Okay. So for constant over I. So now since summation pi xi equal to w, so this implies that pi xi is w by n, okay, and that implies that xi star is w by npn, okay, and yeah, so we will also get lambda star to be 1 by pi xi, sorry, in pi, sorry, yeah, okay, w by npi, okay. So note that lambda is just 1 by pi xi, so you will have lambda star as n by w, and of course we have already assumed that mu star is 0, right. So yeah, mu star is 0 because yeah, so we want the complementary slackness conditions will need mu I xi to be 0, right. So xi is not 0, right, but so mu i's have to be 0. So this is the answer, xi star is equal to w by npi, and lambda star is n by w, and mu star is 0, okay. So just to check if we got the same answer here, right. So in this problem, right, you can see that this was the answer, x1 star is w by 2 p1 and x2 star is w by 2 p2. So and you can recall that here we had w by npi, right. So so when n is equal to 2, you have w by 2 p1 and w by 2 p2. Of course lambda 1 star is different because yeah, the problem that we have considered is slightly different, right. So yeah, if you had considered this problem, the lambda star would be slightly different, okay, nevertheless. So but for this problem, the logarithm problem that we had just considered, we have lambda star is n by w, okay. All right. So I mean we will now try to write a code using augmented Lagrangian method. So if you are asking what is the difference between the earlier examples and this, right. So I mean, is it just another example that we work out with augmented Lagrangian method? Yeah, it is another example. The difference is that we are actually solving for any general n, okay. So that is if I mean you can just modify certain parameters and that is modify the value of n, modify the value of pi's, right, and make some very small modifications, right, and you will actually see that yeah, the code that you are going to write works for every n and every set of pi's that we are going to give, okay. So fine, let's go ahead with that, okay. So yeah, so since the base structure is going to be the same, we will yeah, just copy down this code as such and then make modifications, okay. So we will write down the title as augmented Lagrangian method for utility maximization, yeah, that should be fine, okay. So now f of x is actually the negative of sum of log of xi's, right. So we will write it this way, np dot sum of np dot log of x, okay. So x will be a vector, so np dot log of x will again be a vector, and you are summing those vectors and you have a negative sign in front, okay. So that is just minus log of x1 minus log of x2 minus dot 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 minus log of xn, okay. So yeah, g of x is slightly tricky since you have n plus 1 constraints, right. So yeah, the last n constraints is just minus x1 minus x2 dot 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 minus xn, right, and the first constraint is summation pi xi minus w, right, and all less than or equal to 0, okay. I am going to write it this way, So I am going to have, so this is n, so but n we can write it as the size of x. So the size of x is np dot shape of x of 0. Okay. So this is the negative I of n comma n. So at before the 0th row, right, we need to insert the vector p, p1 p2 dot 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 pn. Okay. So we will write it this way. Okay. And yeah, now the gradient is, okay, oh, so I'm sorry, it's not a matrix. So yeah, this is actually x minus x. So okay, fine. Yeah, I'll have to insert the insert command should come, insert with identity should actually come here. Yeah, so sorry for that. Yeah, and here as well it has to be p dot of x minus w. Okay, and here it will be p. Okay, and here you don't need a 0. Yeah. So to clarify what's going on, so we have n constraints, right? So one of them is the first one is summation pi minus w. The next n of them are minus x, minus x1 minus x2 dot 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 minus xn. So if you write the vector minus x, it is minus x of 0 minus x of 1 dot 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 minus x of n minus 1, right? So with minus x below, I am inserting in the beginning p dot x minus w. So if you differentiate this, you will have minus I at the end, and the first row you will have p. So that's exactly what I have done here for g of x and grad g of x. Okay. Now for L, yeah, so L the command is the same. Now yeah, for grad, so this is going to be minus 1 by x. So I will just change that. The others are going to be the same, and here again it's going to be 1, so it's a diagonal matrix consisting of 1 by x squared, right? So I will just write np dot diag of 1 by x squared. Okay, fine. Now yeah, we will have to define what is p and w, right? So we will consider a 4-dimensional problem, or rather a consumer buying 4 items. Okay, the price of item 1 is 4, price of item 2 is 3, price of item 3 is 2, and price of item 4 is 1. Okay, so I am just going to write this as 4 3 2 1. Okay, and let's say the wealth that he has is 120. Okay, so since it's a 4-dimensional problem, x has to have 4 values, and it's not good to start with 0 because log 0 is not defined. So we will start with 1 maybe. Okay, and the number of constraints is 4 plus 1, 5. So here you can start with all zeros, let's say 5 zeros. Okay, and gamma is 1 and k is 0, and here there is a problem because yeah, so you only have x of 0 and x of 1, right? So instead we will actually just print x, and yeah, I think x should be fine. Okay, and here again we will just print k and mu. Okay, I think that should be fine. Yeah, I think x can also be written. Okay, k, x and mu. Okay, so just to clarify what's going on, I have a specific case of this problem where I have p1, p2, p3, p4 as 4, 3, 2 and 1. I have w as 120. Okay, so in that case it's very clear that x star is going to be 120 by 4 into 4, right? So that's 120 by 16, which is 7.5, and this will be 120 into 120 by 4 into 3, that's 120 by 12, that's 10. So this is 120 by 8, which is 15, and this is 120 by 4, which is 30. Okay, and lambda star is 4 by 120, which is 1 by 30. 1 by 30 is 1 by 30 is fine. Maybe I just have to write 0.0333. Okay, and mu stars are all 0. So we are just going to verify if we are going to get the solution. Okay, so let's do that. Oh, okay, it has to be m and not mu. Yeah, so in 2 steps we have got the solution. Yeah, so 7.5, 10, 15 and 30, and if you see mu, it is 1 by 3 and all zeros, right. So yeah, that was the answer that we were looking for, right. So yeah, but that is for the specific value of P and W that I just gave. So what if we had a different set of P and W, right, and in fact the value of n could also be different. So we are actually having a consumer buying 4 products, right, 4 items. So yeah, let's make it 5 items. Okay, and yeah, let's just add 5 here, and so yeah, maybe let's make this 360. Okay, so now if you are actually finding the answer, yeah, so if so this is case 1, right. So in case 2 we have P is 54321 and W is 360, right. So X star is going to be 360 by 25, right. So W by NPI, right. So 360 by 25 will be, so it is 14.4, and next is 360 by 20, which is 18. Next is 360 by 15, right. So that is going to be 24, and next is 360 by 10, which is 36, and next is 360 by 5, which is 72. And now lambda star is 5 by 360, right. So that is 1 by 72, right. So yeah, that will be about 0.01. Okay, yeah, we can find it out from the code. Yeah, not very difficult, right. So yeah, so 1 by 18 should be 0.5, so divided that you get yeah, I think about 1.3 and possibly 8 if I remember right. Yeah, okay, so let's check if that works. Fine, yeah, let's, and yeah, but now I have to modify this as well. X is the starting point is 5 ones and mu is 6 zeros, right. So let's check if it works. Okay, so yeah, you have the answer here: 14.4, 18, 24, 36 and 72, right. 14.4, 18, 24, 36 and 72, and yeah, so this is 0.0138, which yeah, I think I computed it as such, right. So that's, I mean, here again we are getting the answer. So the beauty of this particular code is that yeah, we have written a code for any general n, right. So I mean, yeah, the previous ones whatever we had worked with are actually for very specific problems where the value of n is very clearly known and the number of constraints is very clearly known, right. So but this is a code that has been written in general for any n, any p and any w, right. So you can give the values of p and w, you can also change the sizes of p and w. Okay, you just have to modify the initial values of x and mu. So that is something you have to note. I mean, not just modify p and w and stay as such. If you are modifying the dimension, right, so you also have to modify x and m here, right. So I mean that can also be changed. I mean, you can modify this as np dot ones of the shape of p, right. So that is one other way of doing it, so that I mean you avoid changing this as well. Okay. Nevertheless, I mean I think you can get that done, not a big problem. Okay. But please note that we are able to solve a very general problem where you have n items to buy, that is the size of n can be any general, right, any general value, and if you just modify p and w and the initial values of x and mu, you get the right answer, right. So you can try with various values of p and w, and the dimensions on can also vary. So fine, this is an example that I wanted to work out. Okay. In the next lecture, so I would like to let you know some things about the linear programming problem. Okay. So I think initially even before starting with the quadratic penalty method in week 7, right. So we discussed about the differences between the linear optimization problem and non-linear optimization problem, and we said that for non-linear optimization problem we are actually going to discuss these two methods, quadratic penalty method and augmented Lagrangian method, right. So what happens if we use this for linear programming? It appears to be general enough, right. So told that the linear programming is something where your objective function is linear and your constraints are linear, right. So if you recall that particular part, right, yes. So in this case, so you can see that so a linear optimization problem in constrained setting, right. So your f is of the form C transpose x, your GIs are of the form A transpose x minus BI, and your HIs are of the form AJ bar transpose x minus BJ bar, right. So what is the problem? I mean, so both of these methods seem like accommodating these kind of problems, right. So you instead of your f of x, gi of x and hj of x, you just have to substitute these kind of equations, right. So why is that a problem at all, right. So that I will let you know in the next lecture. In most of the cases you will see that in these methods when you use these two methods, quadratic penalty method and augmented Lagrangian methods, you will actually not get the answer for a linear programming problem. You need a separate set of algorithms for linear programming problems. So I will explain that in the next lecture. Thank you.